Right here we're looking at section 2.4, and this is really where we take those quadratics that we've been working on and model some real life situations with them. So our learning targets, first we're going to write equations of quadratic functions using vertices, points, and x-intercepts. So in our last section we looked at when I have either the focus or the directrix and the vertex, how do I write the equation? Now you have to do it without the focus or the directrix. And then we're going to write some quadratic equations to model data sets, and I'm going to show you a couple of different ways to do that. So first thing we need to know is there are several different forms that we can have our quadratic in. We can also look at standard form, right? And standard form is our ax squared plus bx plus c. This is what we call standard form. We don't see standard form a lot when we're dealing with graphs, but we'll see it a lot when we're dealing with some other kinds of functions. Okay, we also have vertex form, right? And vertex form is where we have that h and k. And then we can also use intercept form, right? And we're dealing with our x-intercept. So this p and q would be where my equation, where my graph crosses the x-axis. That's really what we're looking at here. These are the two places that it crosses the x-axis. And we'll look at some examples of these. Then if we have 3 or more points, we can either write and solve a system of 3 equations, which is how your book walks you through it. I'm going to walk you through it using Desmos, and you can also use your graphing calculator if you have that as well. It doesn't matter so much to me that you can solve this system. I really want you to be able to use the technology that's available to you. Okay, so here we go. Here's our first one. And you'll notice that we're dealing with a lot of word problems here because these are our real life situations. So the graph shows the parabolic path of a performer who was shot out of a cannon, where y is the height in feet and x is the horizontal distance in feet traveled from the cannon. So write an equation of the parabola. So that's really what we're doing first. And then I know that he lands in a net 90 feet from the cannon. So then we have to figure out the height of the net. So first things I want to look at is I see that here my cannon is starting at 15 feet off the ground because that's where we're launched from. I see here I'm given the vertex and I see that I start to come down. So since I have the vertex, I'm going to go ahead and use my vertex form. So y equals a times x minus h squared plus k. So the things I need in order to write this equation are my a, h, and k. Well, I have h and k right here because my vertex is always h comma k. So I can rewrite that. So y equals a times x minus 50 plus 35. So now I need something else to help me finish out this equation. I don't know what a is, but I see here I have this other point. I have an x and I have a y. So let's plug those in. So my y value in that other point was 15 equals a. My x value was 0 minus 50 squared plus 35. Well, now that I've gotten rid of all of the variables except for a, now I can go ahead and solve. So I have 15 equals a. 0 minus 50 is a negative 50, and a negative 50 squared becomes a positive 2,500 plus 35. Well, the first thing I have to do is subtract that 35 from both sides, and then I can continue to solve. So when I subtract that 35, I end up with a negative 20 equals 2,500a. Well, now I'm going to divide by 2,500 because my goal here is to get a by itself, so I'm dividing by 2,500. So a equals, I see here I've got a 0 on both, so I can get rid of that. I know that 2 goes into 250 125 times, and it was negative. So now I want to look and double check that it makes sense to me, right? That I have a negative a value. Well, yeah, that makes sense because it's opening down, and then it's kind of a big fraction, right? And we talked that fractions make it kind of bigger and skinnier and shorter and fatter, so that's a little short and fatter. So now I can go ahead and finish writing the equation. So now I take all of the information that I have. So I have y equals, my a value is a negative 1 over 125 times x minus 50 squared plus 35. This is the final equation that I can write because I've now written that equation for that parabola. So the second piece I was asked was I was told the performer lands in a net 90 feet from the cannon, and what is the height of the net? Well, I know that the horizontal distance away is going to be my x, so I go ahead and plug this 90 in for my x. So I've got y equals negative 125, 90, I plug that in, and I can just use my calculator now to solve this y. So once you plug this into your calculator, you see that y is approximately 22 feet. Okay, so I just took this information with the x value that I was given once I've written my equation, and I can find my y value. Okay, so now let's look at when I'm not given the vertex. How can I write this equation? So I can follow a very similar path, except since I'm not given the vertex here, I'm going to be using my intercept form here, right? Because I'm given the two intercepts. So my intercept form is y equals a times x minus p times x minus q. And remember that p and q are just those intercepts. So let's plug in the things that we know. I have those intercepts. So y equals a times x minus, here's one of the intercepts, 4. And the other intercept is at 24. So I can just plug those things in. So the other thing I need, just like I did in the last example, was I need an x and a y. And that's what I get from this other point here. So I plug in my 9.6 for my y, and I plug in my 0 for the x. So now I can just simplify. So I have 9.6 equals a times a negative 4 times a negative 24. And then I just continue to simplify my math. So I know a 9.6 equals a negative times a negative is a positive, 4 times 24 is 96. So now let's divide both sides by 96. So I know that a equals a 0.1. And again, I double check. Is this going to be positive? Yes. This is also less than 1, so it's going to kind of be short and fat, and that is true as well. So now I can rewrite my equation. And to do that, I can go back up to here. So my equation is going to be y equals, I plug in that a value, 0.1, and then I have my x minus 4 and my x minus 24. There is my equation. Now I'm asked, what is the coldest temperature? So I know the coldest temperature is going to be the minimum. And I know that the minimum comes when my x value is exactly halfway between my two intercepts. So I go from 4 to 24, and I want to find the middle. And I know that the middle of that is going to be when x equals 14. So I can plug in an x equals 14 for both of these x values, right? And I found that because that's the middle. So I plug that in and I end up with y equals a negative 10. So let's just double check. Does that make sense? Well, yeah, because according to my graph, it should be right about negative 10, and it ended up being exactly negative 10. So that is my vertex. The vertex becomes 14, comma, negative 10. And I was asked that to find the coldest. So now let's look at part B. Part B here, we're looking for average rate of change. And you're going to be seeing this a lot. Let me just erase what we're doing up here first. Okay, so average rate of change is an easier way that we can compare parts of our function. So I want to compare the average rate of change. So the average rate of change is really, in fact, the slope between 2 points. We don't want to just say find the slope of this, because that leads into much more complicated things, because it's a curve and it does not have a slope. But I can take my 2 points and I can find the slope between them. And that is called the average rate of change. So I'm asked, what is the average rate of change in temperature over the interval in which the temperature is decreasing? So you'll see I have my 2 points, and I found my vertex, which was at 14, negative 10. So now that I have those points, I can go ahead and find my average rate of change. So I know I'm dealing with my vertex, which was 14, negative 10, and I'm also dealing with that first point, which was 0, 9.6. So now I can find my average rate of change, and to do that I just find the slope. So I know to get from a negative 10 to 9.6, I have to go up 19.6. To get from 14 to 0, I go down 14. So now I just plug this into my calculator, and I end up with approximately, it's going to be a negative slope, approximately negative 1.4. So this is the average rate of change when it was going down, decreasing. Now I'm asked when it's increasing. Okay, so I know I'm still going to be using my vertex, which was at 14, negative 10, but now I want to use the other point that I'm given when I finish increasing at 24, 0. So I can do the same thing to find my slope. To get from negative 10 to 0, I go up 10. To get from 14 to 24, I go up 10. So my slope here is 1. So now comparing my slopes, I can say that my average rate of change, right, is greater than when it's decreasing than when it's increasing. Even though this is negative, 1.4 is a larger number than 1. So now I can just use these two numbers to compare anything I'm asked about. Okay. So now let's look at this. I'm not really given the vertex and I'm not given the intercepts. So in your book, if you look, this problem can get long and complicated because I can take any three of these points, I can set up a system of equations, and I can solve. So if you're interested in that, come find me and we can do that. Or if you'd rather use Desmos, you sure can. So what I've done here is I've plotted all of these points in Desmos. And I know that we're dealing with a quadratic here, so I can go ahead and use my quadratic regression. So I'm going to have y1, and remember it's not equal to, and I've got my ax1 squared, plus bx1 plus c. So now that I have this, I can see that my r value is exactly 1, so I know it fits my data perfectly. Now I'm given both all my a, b, and c, so I can rewrite my equation. So now the equation of this line is going to be my y equals, it was negative 11x squared, and then my b was 700, and then my c value was 21,000. Okay, so I can either go through all the steps and solve a 3-variable system, or I can use Desmos to help me as well. So now that I have my equation, I can answer this second part of the question. So after about 20.8 seconds, passengers begin to experience a weightless environment. Write and evaluate a function to approximate the height. So well, now I've written this, so now all I have to do is take this 20.8 and plug it in, there's another x right there, anywhere I see that x. So once you do that and just plug it in, then you'll get your approximate height in which that occurs. And I'm not going to do this right now. This is something you can do. Just plug in this 20.8 anywhere you see an x. Okay, so here's our next example, and we're going to do something very similar. So here I see I have a table of values, so I do not have my intercepts and I'm not told for sure what my vertex is. So I'm going to use Desmos. So when I put that data in Desmos, it gives me an approximate equation for this function. It's not exact because this does not model exactly a parabola, but it's pretty close. So now I can just plug those values into Desmos and find my equation. Now once I have that equation, I can actually use it to mathematically find the optimal. And when I see the word optimal, that either is going to mean maximum, minimum, those kinds of things. Okay, so to find the optimal driving speed, so I can use my equation to find that. Or I can use the graph. And when I have that graph in Desmos, if I click where I think the maximum is, it will actually give me the point. So then I can use that point to give me my actual driving speed. So let's take a look at that. So here now you'll see in Desmos this new table with all of that same data. I use my same quadratic regression. I see that my r value is not exactly 1. That's because these points are all close to, but not exactly on the line. But so here I'm given my a, b, and c, so I can write my equation, right? And now I'm asked for the optimal. So when I'm looking at Desmos, you see this kind of like lighter point. This is going to be my maximum. So this tells me the optimal driving speed that I need for that equation. Okay? So it asked me the optimal speed, and I know that speed was my miles per hour, which is my x value, so I can say that my optimal speed is going to be about 48.5 miles per hour, and that will give me my optimal driving speed. So I can go ahead and use my technology to help me out here. So these next few are just problems that you may want to try on your own. Make sure that you can do it and that you know what you're looking at. So what I would do here is definitely graph these first and see what you come up with. So again, here I have a couple of tables. Put these in Desmos or your graphing calculator. See if it gets you what you need to. So now let's look back at our learning targets. First we looked at equations and we wrote equations of quadratic functions using vertices, points, and intercepts. And we always take that extra point and use that as our x and y value. And then our second learning target was to write quadratic equations to model data sets. And that you can absolutely do using technology and Desmos to help you. So now that you've gone through these learning targets, go ahead and work on your homework for this section.